Imagine something so massive it makes our entire galaxy look like a grain of sand. What if I told you there are objects in the universe that are billions of times larger than anything we've ever known? In this video, we'll embark on a journey to discover the largest things in the universe, from stars and galaxies to unimaginable cosmic structures that defy our understanding of size and scale. These colossal entities don't just amaze us, they hold the secrets to how the universe formed, evolved, and continues to expand. Buckle up for an unforgettable journey through space and time. At the end of this video, we'll uncover the largest structure ever discovered, a cosmic entity so vast it challenges the very laws of physics. Stick around to find out what it is. Let's start close to home, relatively speaking, with planets. These cosmic spheres might feel familiar, but when we venture beyond our solar system, we find planets so massive and extraordinary that they challenge everything we thought we knew about planetary formation. Planets are born in the swirling gas and dust disks around young stars. Over millions of years, particles collide and stick together, growing from tiny pebbles into colossal worlds. For a planet to grow truly massive, it must form in a region rich in gas, where it can rapidly accumulate a thick atmosphere of hydrogen and helium. This has to happen before the star's radiation blows away the surrounding material. These gas giants, like the ones we know in our solar system such as Jupiter and Saturn, are already impressive. But in distant star systems, astronomers have found planets so massive that they defy expectations. These planets, often called super-Jupiters, can reach sizes and masses much greater than Jupiter, our solar system's heavyweight champion. There's a limit to how large a planet can grow before it stops being a planet and starts acting more like a failed star. This boundary, known as the deuterium burning limit, is about 13 times the mass of Jupiter. Beyond this point, the core becomes hot enough to ignite deuterium fusion, marking the transition into brown dwarf territory, a strange middle ground between planets and stars. It's interesting that we have already found some really large exoplanets. None of them comes close to this theoretical limit. While size and mass don't always go hand in hand, some giant planets are less dense, resembling swollen gas balloons. Their sheer scale is still mind-boggling. To understand the sheer size of these colossal worlds, let's start with Earth. Our planet has a diameter of about 7,900 miles, or 12,700 kilometers, a scale that's still relatively easy for us to picture. Now compare that to Jupiter, the largest planet in our solar system, with a diameter of about 89,000 miles, or 143,000 kilometers. That means you could fit over 11 Earths across Jupiter's diameter, and more than 1,300 Earths could fit inside it by volume. Yet, even Jupiter seems modest compared to the gas giants discovered in distant star systems. Imagine super-Jupiters, nearly twice the size of Jupiter, that redefine our understanding of what a planet can be. Among the approximately 5,500 exoplanets discovered so far, one of the largest ones is WASP-17b, located about 1,300 light-years away in the constellation Scorpius. Found in 2009 by the Wide-Angle Search for Planets (WASP) project, this exoplanet is nearly twice the size of Jupiter, despite being only about half its mass. Its bloated atmosphere is believed to result from extreme heating as it orbits perilously close to its parent star, a phenomenon known as hot Jupiter behavior. How close? About 20 times closer to its host star than Earth is to the Sun. WASP-17b completes one orbit in just 3.7 Earth days. Another fascinating giant is TRES-4b, discovered in 2006 by the Transatlantic Exoplanet Survey. It orbits its host star even closer than the previously mentioned WASP-17b. With a radius 1.7 times that of Jupiter, it's among the least dense planets ever found, with a density of approximately 0.2 grams per cubic centimeter, meaning it is less dense than cork. Scientists believe its proximity to its star inflates its atmosphere, making it one of the puffiest giants we've observed. And then there's HAT P67b, one of the most extreme examples of a gas giant. Discovered in 2017 by the Hungarian Automated Telescope Network, HATNET, this exoplanet has a radius approximately 2.1 times that of Jupiter. It orbits around its host star at a distance of only 5.2 million miles, or 8.4 million kilometers. One orbit takes only about 4.8 Earth days. What's even more incredible is its density, or lack thereof. HAT P67b is so puffy and lightweight that scientists estimate its density to be just 0.06 grams per cubic centimetre, less than 1/10 the density of cork. Just like in the case of WASP B17 and TES-4b, its inflated atmosphere is likely due to its incredibly close orbit around its star, where extreme temperatures heat and expand the planet's gases. These planets were discovered using advanced techniques like the transit method, which measures the dimming of a star as a planet passes in front of it. This approach has allowed astronomers to find worlds beyond our imagination, helping us piece together the story of how planets form and evolve in extreme environments. These gigantic planets are more than just cosmic curiosities. They're windows into the process of planetary formation and the diversity of the universe. They challenge our understanding of how planets grow, survive, and evolve in extreme conditions. And they remind us that the universe is capable of creating objects far beyond the limits of our imagination. As we continue our journey, keep these planetary giants in mind. They're just the beginning, because the universe has much larger surprises in store. From colossal planets to stars that could engulf our entire solar system, the universe's largest stars are a class of cosmic phenomena that stretch the limits of size and power. These hypergiant stars are more than just massive. They're among the most fascinating and influential objects in the cosmos, driving the evolution of galaxies and shaping the universe as we know it. Stars form when immense clouds of gas and dust collapse under their own gravity, igniting nuclear fusion at their core. Most stars, like our Sun, reach a stable size where the outward pressure from nuclear fusion balances the inward pull of gravity. But some stars are born in regions of space so rich in gas that they can grow far beyond this balance, becoming what we call hypergiants. These stars are the universe's heavyweights, at least when it comes to stars, consuming vast amounts of hydrogen at their cores and burning through it at an astonishing rate. They're so luminous that their radiation can blow away surrounding gas, creating vast stellar winds and unique environments for future star formation. To truly grasp the scale of hypergiant stars, it helps to stack them up against each other and against something more familiar, like our Sun. The Sun, with a diameter of approximately 870,000 miles, or 1.4 million kilometers, seems vast compared to Earth, which has a diameter of just about 7,900 miles, or 12,700 kilometers. You could line up 109 Earths across the Sun's diameter, but even the Sun pales in comparison to the monstrous stars lurking in our galaxy and in the universe. Let's start with a star you might know, or at least might have heard of. Betelgeuse, the bright red shoulder of the constellation Orion. Betelgeuse is a red supergiant. It is one of the largest stars visible to the naked eye, thus it has been known since antiquity. It has a radius about 764 times that of the Sun. Yes, you've heard it right. It is more than 700 times larger than our already unimaginably large Sun. It means that its diameter is about 1 billion miles, or 1.6 billion kilometers. If Betelgeuse replaced the Sun, its surface would reach beyond the orbit of Mars, swallowing Mercury, Venus, Earth, and even the asteroid belt. Despite its immense size, it is estimated to weigh only about 10 to 20 times more than our Sun. How is it possible? The answer is simple. Betelgeuse, like all red supergiants, is much less dense than our own host star. Today, Betelgeuse is understood to be nearing the end of its stellar life cycle. It will eventually explode as a supernova, possibly within the next 100,000 years. This will mark the end of its remarkable journey, as it is one of the most studied and famous stars due to its size, brightness, and the mystery surrounding its fate. Even larger than Betelgeuse is Antares, the heart of the Scorpius constellation, about 550 light-years away from us. Antares, also a red supergiant, has a radius about 883 times that of the Sun, and a mass between 12 and 15 times that of the Sun. If it were placed at the centre of our solar system, its outer layers would stretch just shy of Jupiter's orbit. Its name, derived from Greek, means rival of Mars, referencing its reddish hue. However, its size and brightness eclipse any comparison to the red planet. It is a true giant of the cosmos. Like other massive stars, Antares is nearing the end of its life. In a few million years, it is expected to explode as a supernova, an event that will be visible across the galaxy. When this happens, it will briefly outshine the entire rest of the Milky Way. This explosion will mark the final stage of its life cycle, where it will shed its outer layers and leave behind a dense core, potentially forming a neutron star or a black hole. Next is UY Canis Majoris, once considered the largest known star. Located about 4,900 light-years away in the constellation Canis Major, this red hypergiant has a radius approximately 1,420 times that of the Sun. That's a diameter of about 1.24 billion miles, or 2 billion kilometers, large enough to engulf the orbit of Saturn. If you were to board a jet traveling at 560 miles, or 900 kilometers per hour, and fly around UY Canis Majoris, it would take you over 1,100 years to complete the journey. This hypergiant is extremely luminous, emitting over 200,000 times the luminosity of the Sun. Its brightness, however, varies due to its pulsating nature, a feature common among red supergiants. Another interesting fact about UY Canis Majoris is that it experiences significant mass loss through strong stellar winds, which can blow away up to 10 millionths of a solar mass per year. This mass loss helps to shape the surrounding nebulae, and it has left a large shell of gas and dust around the star. Then there's UY Scuti, another red supergiant, located in the constellation Scutum. It has a radius about 1,700 times that of the Sun, making its diameter over 1.49 billion miles, or 2.4 billion kilometers. If UY Scuti were the Sun, its surface would stretch beyond Jupiter's orbit. Despite its size, UY Scuti is relatively faint when viewed from Earth because of its distance of roughly 9,500 light-years. UY Scuti is even more luminous than UY Canis Majoris. It emits about 340,000 times the luminosity of the Sun. This star was once believed to be the largest, but, believe it or not, recent measurements suggest even bigger stars might be lurking in the cosmos. Finally, we arrive at Stephenson 218, not surprisingly another red supergiant, discovered in the Stephenson 2 star cluster, almost 20,000 light-years from the Earth. Stephenson 218 was first catalogued in the 1960s by Harvard astronomer and stellar cataloguer Richard Stephenson, who was studying a group of stars in the Scorpius constellation. It was originally catalogued as part of the Stephenson 2 star cluster. At first, Stephenson 218 was not recognized as one of the largest stars. It was part of a broader study of stars in the cluster, and its true size became apparent only with more detailed observations in the latter half of the 20th century. This behemoth has a radius of approximately 2,150 times that of the Sun, making its diameter an astonishing 1.86 billion miles, or 3 billion kilometers. If Stephenson 218 replaced the Sun, it would engulf not just Jupiter's orbit but also Saturn's. The exact size of Stephenson 218 and other mentioned giants is still debated due to the difficulties in measuring stars with such vast sizes, and its radius can vary slightly based on different observation methods. Imagine our solar system as a swimming pool, with the Sun as a beach ball. Stephenson 218 would be a sphere the size of an apartment building towering over it. While stars like Stephenson 218 and UY Scuti dominate in size, their enormity raises fascinating questions about their existence. How do they form? How do they remain stable? These hypergiants are rare because their massive sizes make them unstable, shedding tremendous amounts of mass through powerful stellar winds. To put their size into an even grander perspective, our entire solar system is about 287 billion kilometers across, including the outermost reaches of the Oort cloud. Stephenson 218's diameter is roughly 1% of that distance. seemingly small on a cosmic scale, but utterly enormous when compared to any single object. These stars remind us of the incredible diversity in the universe, showing that while our Sun sustains life, it is but a speck compared to these cosmic giants. One of the most striking differences between hypergiant stars and smaller stars like our Sun is their lifespan. While the Sun is expected to shine for about 10 billion years, hypergiants live for only a few million years, a mere cosmic blink of an eye. The reason for this short lifespan lies in their size and energy output. Hypergiants are massive engines of nuclear fusion, burning through their fuel at an astonishing rate. In the core of a star, hydrogen atoms fuse into helium, releasing immense amounts of energy in the process. For stars like the Sun, this process happens relatively slowly, allowing them to sustain themselves for billions of years. In hypergiants, however, the immense gravity and pressure in their cores drive fusion at a far more intense rate. These stars radiate energy millions of times more powerfully than the Sun, rapidly depleting their reserves of hydrogen. As a result, they burn bright but live fast, exhausting their fuel in just 3 to 10 million years, depending on their initial mass. The larger a star, the more intense the pressure and temperature at its core. This increased pressure accelerates the fusion process, causing the star to produce energy at an exponentially faster rate. For hypergiants, this process is so extreme that they not only burn through their hydrogen reserves quickly, but also begin fusing heavier elements like helium, carbon, and oxygen much sooner than smaller stars. This rapid progression through the stages of stellar fusion leads to instability. As the star nears the end of its life, it can no longer produce enough energy to counteract the immense gravitational forces trying to collapse it. The result is a spectacular and violent death, often as a supernova. In contrast, the Sun will remain stable in its main sequence phase for billions of years, fusing hydrogen at a more measured pace. After exhausting its hydrogen, it will swell into a red giant and shed its outer layers, eventually leaving behind a dense core known as a white dwarf, a far less dramatic fate compared to the explosive end of a hypergiant. This dramatic contrast in lifespans highlights the delicate balance between mass, fusion, and energy in determining a star's ultimate destiny. Hypergiants, though short-lived, leave a lasting legacy by seeding the cosmos with the heavy elements forged in their fiery cores, playing a crucial role in the life cycle of the universe. Stars like UY Scuti and Stephenson 218 were discovered relatively recently, thanks to advancements in astronomical technology. UY Scuti was first catalogued in 1860, but its true size wasn't appreciated until modern telescopes allowed for precise measurements of its distance and luminosity. Similarly, Stephenson 218 was identified in 1990 as part of a massive star cluster in the constellation Scutum. Using tools like spectrometry and parallax measurements, astronomers determined the sheer scale of these stars, uncovering their role as cosmic behemoths. Observatories like the European Southern Observatory, ESO, and space telescopes such as Hubble have played a vital role in studying these distant giants, shedding light on their structure, composition, and life cycles. To fully appreciate these stars, consider this. While UY Scuti and Stephenson 218 are astonishingly massive, they are far from unique. There may be even larger stars hidden in the distant reaches of the cosmos, waiting to be discovered. Each of these stars is a monument to the universe's ability to create on an unimaginable scale, reminding us of the vastness and power of the cosmos. Hypergiants are more than just astronomical curiosities. They are crucial to the story of the universe, both its past and its future. They've helped shape galaxies, forged the elements that make up our world, and left behind remnants like black holes that continue to influence the universe today. As we continue our exploration of the universe's largest entities, we delve into the colossal black holes that lie at the heart of galaxies. These supermassive black holes with masses millions or even billions of times greater than our Sun defy comprehension and rewrite our understanding of gravity, space, and time. But first, let's take a quick look at what a black hole is and what types of black holes we are currently aware of, or believed to have existed in the past. Black holes are regions of space where gravity is so strong that not even light can escape. Imagine a point in space where the force of gravity is so intense that it crushes matter and energy into an infinitely small, dense point known as a singularity. Surrounding this singularity is the event horizon, the point of no return, where the gravitational pull becomes irresistible. There are actually several different types of these mysterious objects, each with its own unique characteristics. Stellar black holes are the most common type, formed when massive stars run out of fuel and collapse under their own gravity, like the previously discussed red supergiants. The core of the star implodes, and if it's massive enough, it turns into a stellar black hole. Typically, these black holes have a mass between 3 and 10 times that of our Sun. Intermediate black holes are harder to detect and measure, but they are believed to exist in a size range between stellar black holes and supermassive black holes. Their masses can range from hundreds to thousands of solar masses. They might be the result of 2 or more stellar black holes merging, or through the collapse of clusters of stars. Supermassive black holes are giants that can weigh millions or even billions of times the mass of the Sun. These are by far the largest types of black holes. These objects sit at the centers of most galaxies, including our own Milky Way. It's thought that these black holes formed early in the universe's history and grew over time by consuming nearby stars and gas, becoming the enormous objects we see today. Primordial black holes are theoretical objects that are believed to have formed shortly after the Big Bang, potentially in the first moments of the universe's existence. They could have masses ranging from tiny subatomic levels to stellar masses, and they remain the most speculative and mysterious types of black holes, as we currently have no direct evidence for their existence. As already mentioned, at the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These black holes play a pivotal role in galaxy formation and evolution by regulating star formation and dispersing energy through the surrounding environment. When a supermassive black hole feeds on nearby matter, it can create an accretion disk, a swirling, superheated ring of gas and dust. The friction in this disk generates immense amounts of energy, often outshining the entire galaxy and creating what we observe as quasars, or active galactic nuclei, also known as AGNs. These energetic outbursts can heat surrounding gas, suppressing star formation and influencing the galaxy's structure. Supermassive black holes exert a stabilizing gravitational pull, anchoring their galaxies. Without them, the delicate balance that holds galaxies together might not exist. Supermassive black holes are some of the most awe-inspiring entities in the universe. To truly understand their scale, it's helpful to compare them not only to more familiar objects like our Sun, but also to each other, as their sizes and masses can vary dramatically. Let's explore these titans in order of size, starting from the relatively modest and ending with the true giants. At the heart of the Milky Way, about 26,000 light-years from Earth, lies Sagittarius A, a supermassive black hole with a mass of about 4 million suns. Its event horizon is roughly 14.6 million miles, or 24 million kilometers in diameter, smaller than the distance from Mercury to the Sun, but still incomprehensibly vast. Despite being dwarfed by larger black holes, Sagittarius A plays a crucial role in anchoring our galaxy and influencing the orbits of stars near its core, such as the famous star S2, which completes a close elliptical orbit around it in just 16 years. Sagittarius A was the second ever black hole imaged in 2022 by the Event Horizon Telescope, or EHT. Let's see which one was the first ever imaged one, a true giant compared to the one in the middle of our home galaxy. In 2019, so 3 years before Sagittarius A was imaged, the Event Horizon Telescope captured the first ever image of a black hole, M87, located at the center of the galaxy Messier 87. The first evidence of M87 came from observations of the galaxy in the 1960s, when astronomers noticed unusual high-energy emissions from the center of the galaxy. Over time, it became clear that these emissions were powered by the active black hole at M87's core. This supermassive black hole has a mass of about 6.5 billion suns and an event horizon with a diameter of approximately 25 billion miles or 40 billion kilometers, large enough to encompass our entire solar system multiple times over, as the furthermost planet, Neptune, is about 4.15 billion miles away from the Sun. To put M87's size into another perspective, its diameter is about 270 astronomical units, one astronomical unit, or AU, being the average distance between the Earth and the Sun. M87's immense gravitational influence drives powerful jets of particles that extend for thousands of light years, shaping the galaxy and the surrounding intergalactic space. If you thought that black holes cannot get any bigger, you were wrong. Let me introduce ultramassive black holes, a subcategory for supermassive black holes that exceed 10 billion solar masses. The first object of this category that we are going to take a look at is Holm 15A. Located in a galaxy cluster about 700 million light-years away, Holm 15A is one of the largest known black holes, with an estimated mass of 40 billion suns. Its size is so extreme that its event horizon could span about 150 billion miles, or 240 billion kilometers, dwarfing most other black holes. 150 billion miles equals approximately 1,614 astronomical units. The size of this object is truly unimaginable, but still not enough to make it the largest known black hole. TON 618 is probably the most well-known ultramassive black hole, previously the largest known one, before the last Titan took its place. It is a quasar that emits so much light and energy that it outshines entire galaxies. It was discovered in 1957 as part of a survey for blue stars. In 1970, due to follow-up observations, it was identified as a quasar with a supermassive black hole in the middle. Scientists first tried to estimate its mass in the 1980s and 1990s. The current mass estimate was done later, around 2004. As far as we know today, it has a mass of approximately 66 billion suns, with an event horizon stretching to about 242 billion miles, or 390 billion kilometers, in diameter. To put this into perspective, light would take over 36 hours to travel across its event horizon, a stark contrast to the Sun, which light crosses in just 4.6 seconds. TON 618's immense energy output is due to the vast amounts of matter falling into its accretion disk, making it one of the brightest objects in the observable universe. The central black hole of the galaxy, IC 1101, one of the largest known galaxies, is estimated to have a mass exceeding 40 billion solar masses. IC 1101 itself spans over 6 million light-years, approximately 60 times the diameter of the Milky Way, and its black hole is proportionately massive, potentially rivaling TON 618 in size. It's probably a bit less massive than TON 618, but at the moment we don't know for sure. We need some more time and data to calculate more precise estimations. Last but not least, let's take a look at the Phoenix Cluster Black Hole, also called Phoenix A. Situated at the center of the Phoenix Cluster, about 5.7 billion light-years away, this supermassive black hole is not only massive, but also extremely active. Its accretion processes release enormous amounts of energy, creating jets and heating the surrounding gas to prevent star formation. This interplay between the black hole and its cluster environment highlights the critical role these giants play in regulating galaxy clusters. But what about its size? Estimates vary, but currently Phoenix A is believed to be the most massive known black hole, with a mass possibly reaching 100 billion solar masses, ever more than the previous record holder, TON 618. Can black holes get even bigger? Possibly. While Phoenix A currently holds the title as the most massive confirmed black hole, some theoretical models suggest even larger black holes could exist in the distant universe, hidden within ancient massive galaxy clusters. These ultramassive black holes could potentially exceed 100 billion solar masses, their event horizons spanning light days in diameter. Such black holes would challenge existing models of black hole growth and galaxy formation. As we journey further into the realm of cosmic giants, we encounter the largest galaxies in the universe, enormous collections of stars, gas, dust, and dark matter that defy imagination. These colossal structures not only dwarf our Milky Way, but also play a key role in shaping the cosmic web, the vast network of matter that defines the universe's large-scale structure. Galaxies grow through processes like mergers, accretion of gas, and star formation. Over billions of years, smaller galaxies collide and merge, forming larger and more complex systems. This will happen to us in the future when the Milky Way and the Andromeda Galaxy will collide and merge. It is currently 2.5 million light-years away from us, but it's moving toward our galaxy at a speed of about 68 miles, or 110 kilometers per hour. The largest galaxies often reside at the centers of galaxy clusters, where frequent interactions with other galaxies feed their growth. These giants are typically elliptical galaxies, characterized by their rounded, featureless shapes and immense size. Now let's take a look at some of the largest galaxies we know and can measure. Let's start with our own to understand just how large these galaxies can be. We are then going to compare its larger siblings to it to put their immense size into perspective. The Milky Way is a barred spiral galaxy with a diameter of about 105,000 light-years and contains roughly 200 billion to 400 billion stars. A lesser-known fact is that it is on average about 1,000 light-years thick. It means that it is approximately 100 times wider than thicker. Our home, the solar system, is located about 27,000 light-years from the galactic center, near the inner edge of the Orion Arm. It takes the Sun about 225 to 250 million years to complete one orbit around the Milky Way, a journey known as the galactic year or cosmic year. As we have discussed in the previous chapter, a supermassive black hole called Sagittarius A resides at the center of our galaxy, forming its shape and movement. The Milky Way is incomprehensibly large, yet there exist galaxies that dwarf even this immense structure. Let's leave behind our home and check out some of the true giants. The Condor Galaxy, also known as NGC 6872, is a stunning cosmic giant and one of the largest spiral galaxies ever discovered, stretching an incredible 522,000 light-years from tip to tip. To put that into perspective, it is more than 5 times the size of the Milky Way, which spans around 100,000 light-years in diameter. Imagine stacking 5 Milky Ways end to end. That's how vast the Condor Galaxy is. Located about 212 million light-years away in the constellation Pavo, its immense size is due to a close gravitational interaction with a smaller companion galaxy, IC 4970, which has stretched its spiral arms to extraordinary lengths. These elongated arms are rich with star-forming regions where countless new stars are being born in the aftermath of this galactic tug-of-war. UGC 2885, also known as Rubin's Galaxy, is an awe-inspiring cosmic giant and one of the largest spiral galaxies ever observed, with a diameter of approximately 800,000 light-years. Being 8 times the size of our galaxy, if the Milky Way were a dinner plate, Rubin's Galaxy would be as wide as a city block. Located 232 million light-years away in the constellation Perseus, this massive galaxy is surprisingly calm and stable for its size, quietly rotating and forming stars at a modest rate. Its immense structure and tranquil nature have made it an object of fascination for astronomers. Named in honor of Vera Rubin, the pioneering scientist who provided groundbreaking evidence for the existence of dark matter, this galaxy is a testament to the mysteries of the universe and the monumental forces at play in shaping such extraordinary celestial objects. Rubin's Galaxy reminds us of the vastness and beauty of the cosmos, where even the largest structures can move with elegance and quiet precision. ESO 1465 is a cosmic titan, a supergiant elliptical galaxy located about 1 billion light-years away in the Abell 2319 galaxy cluster. With an estimated diameter of 2.6 million light-years, it utterly dwarfs our Milky Way. Imagine placing 26 Milky Ways side by side. That's the scale of ESO 1465. This behemoth owes its massive size to its location at the center of a galaxy cluster, where it has likely grown through countless galactic mergers over billions of years. Known as a CD galaxy, it possesses an extended halo of stars that blends seamlessly with the intracluster light, creating an enormous diffuse glow that envelops its core. Its dense center is packed with older, redder stars, and the galaxy itself holds a treasure trove of dark matter and ancient stellar populations. ESO 146-5 is not just a galaxy, it's a galactic metropolis, showcasing the incredible power of gravitational interactions in the cosmic tapestry. The Alcyonius galaxy is a jaw-dropping celestial phenomenon and the largest radio galaxy ever discovered, stretching an unbelievable 16 million light-years across. This immense size makes it not just larger than the Milky Way, it's over 160 times its diameter. Located about 3 billion light-years away, its staggering dimensions are primarily defined by its colossal radio lobes, which are formed by jets of high-energy particles blasting out from a supermassive black hole at its center. These radio lobes stretch far into intergalactic space, dwarfing the visible galaxy that houses them. Despite its extraordinary scale, the visible portion of Alcyonius is relatively unremarkable, a quiet and dim elliptical galaxy. Its immense size showcases the incredible power of black holes and the cosmic forces that create such extraordinary structures. Last but not least, the already mentioned IC 1101, the undisputed heavyweight champion of galaxies, an elliptical colossus. It has a diameter of roughly 6 million light-years, making it the largest known galaxy by sheer size, also about 60 times larger than our Milky Way. Found at the center of the Abell 2029 galaxy cluster, about 1 billion light-years away, IC 1101 is the result of countless galactic collisions and mergers over billions of years, which have turned it into a monstrous conglomerate of stars, gas, and dark matter. It's estimated to contain hundreds of trillions of stars, far outshining the approximately 200 billion stars in the Milky Way. The galaxy's central regions are densely packed with older stars, while its outer edges fade into an enormous halo of diffuse light that stretches far beyond what the eye can easily detect. IC 1101 isn't just massive, it's ancient, bearing the scars of a cosmic history written in gravitational battles. The largest galaxies are more than just cosmic curiosities. They play a pivotal role in the cosmic web, the vast structure of the universe composed of filaments of dark matter, galaxies, and gas. Massive galaxies like IC 1101 exert immense gravitational pull, anchoring galaxy clusters and shaping the distribution of matter in their regions. Their influence extends far beyond their visible edges, affecting the orbits of nearby galaxies and the flow of intergalactic gas. Many large galaxies, particularly radio galaxies like Alcyonius, produce powerful jets from their central black holes. These jets stretch across millions of light-years, heating the surrounding gas and preventing it from condensing into new stars. This feedback mechanism helps regulate star formation and maintain the balance of matter in galaxy clusters. In giant elliptical galaxies, the intense radiation and energy from their central regions often heat the surrounding gas, making it difficult for new stars to form. This explains why many large galaxies are composed mainly of older red stars. The largest galaxies are also important because they play a critical role in understanding the universe's evolution and structure. They reveal the effects of dark matter and dark energy, provide clues about the early universe, and highlight the role of supermassive black holes in shaping their environments. As we uncover more about these enormous structures, we gain a clearer picture of the cosmic web and the forces that govern the universe on its grandest scales. As we journey further into the cosmos, we encounter the universe's largest gravitationally bound structures, galaxy clusters. These colossal formations, sometimes containing thousands of galaxies, vast quantities of hot gas, and immense amounts of dark matter, reveal how matter is organized on the grandest scales. Stretching across millions of light-years, these clusters are not isolated. They form interconnected networks that weave the fabric of the cosmic web. The South Pole Wall is one of the most colossal structures ever discovered in the universe, stretching an incredible 1.37 billion light-years across. To put that into perspective, if you could travel at the speed of light, it would still take you over 1 billion years just to go from one end of this structure to the other. That's more than 13,000 times the width of our Milky Way galaxy. This gargantuan cosmic feature is located in the southern sky, hidden behind a region called the Zone of Avoidance, where the Milky Way's dense stars and dust make it challenging to observe distant galaxies. But astronomers used clever techniques, like mapping galaxy motions and their redshifts, to uncover the South Pole Wall in 2020. What makes it truly fascinating is its structure. Imagine a giant interconnected filament of galaxies, clusters, and dark matter, like a web stretching across a mind-boggling distance. It's part of the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. The South Pole Wall's discovery is groundbreaking because it lies so close to us, about 500 million light-years away, which is relatively nearby in cosmic terms. It raises exciting questions about how such massive structures formed and evolved over billions of years, especially given the limits of known physics and cosmology. Following the South Pole Wall, we move on to another colossal cosmic structure that redefines the scale of the universe, the Sloan Great Wall. This vast structure spans an incredible 1.38 billion light-years, placing it among the largest known formations in the cosmos too. Discovered in 2003 using data from the Sloan Digital Sky Survey, the Sloan Great Wall lies about 1 billion light-years away. Despite their name, these structures are not solid walls, but web-like networks of galaxy clusters and superclusters, all bound together by gravity. They are part of the cosmic web, the intricate scaffolding of galaxies and dark matter that stretches across the universe. What makes the Sloan Great Wall so intriguing is how it challenges our understanding of the universe. According to the cosmological principle, the universe should appear uniform on the largest scales, but structures like this, and the South Pole Wall, seem to push the boundaries of that idea. How could something so massive form in just 13.8 billion years, the age of the universe? This is just one piece of a much larger story. As we delve deeper into the universe, structures like the Sloan Great Wall remind us that the cosmos is far more vast and interconnected than we can easily imagine. And yet, there are even larger and more mysterious formations to explore, like the giant GRB ring and the Hercules-Corona Borealis Great Wall. Our journey through the universe's most massive structures is not over yet. Building on the enormity of the Sloan Great Wall, we come to an even more mysterious structure, the giant GRB ring. This remarkable formation spans an estimated 5.6 billion light-years, making it nearly 4 times larger than the Sloan Great Wall. If you thought the previous structures were mind-boggling, this one redefines the limits of cosmic scale. To put it into perspective, its size is more than 50,000 times the diameter of the Milky Way. The giant GRB ring was discovered in 2015, not through visible galaxies, but by tracking gamma-ray bursts, or GRBs, powerful explosions associated with the deaths of massive stars or the merging of neutron stars. These bursts are scattered across the sky in a nearly perfect ring-like arrangement, with a radius of about 2.8 billion light-years. Scientists believe these gamma-ray bursts trace regions of intense star formation, potentially within interconnected galaxy clusters or superclusters. What makes the giant GRB ring so fascinating is its almost eerie symmetry and scale. Structures this vast are difficult to reconcile with our current understanding of the universe's formation. According to existing models of cosmology, structures larger than 1.2 billion light-years shouldn't exist, and yet the giant GRB ring defies this limit, leaving scientists puzzled. This enormous structure challenges the fundamental assumptions about how the universe is organized, suggesting that there's still much we don't understand about the forces shaping the cosmos. From the giant GRB ring, our journey takes us to the end of the video, where we will take a look at the Hercules-Corona Borealis Great Wall, the largest and most extraordinary structure ever discovered. Finally, we arrive at the Hercules-Corona Borealis Great Wall, the largest known structure in the universe. This cosmic behemoth spans an unfathomable 10 billion light-years across. That's nearly 100,000 times the diameter of the Milky Way. If the universe itself were scaled down to the size of Earth, the Hercules-Corona Borealis Great Wall would stretch from one side of a continent to the other. Discovered in 2013 through the study of gamma-ray bursts, GRBs, this massive wall is made up of countless galaxies, galaxy clusters, and dark matter filaments. Gamma-ray bursts, the universe's most energetic explosions, act as signposts that helped scientists map its incredible structure. Located in the direction of the Hercules and Corona Borealis constellations, it stretches so far that light from one end to the other would take nearly the entire age of the universe to travel. The existence of the Hercules-Corona Borealis Great Wall is nothing short of astonishing. Just like its smaller siblings, it challenges the cosmological principle, which posits that the universe should be roughly uniform on the largest scales. Its sheer size leaves scientists questioning how such a vast structure could form in just 13.8 billion years, the age of the universe. From the tiniest details of planets to the monumental scale of galaxy clusters, the universe never ceases to amaze us with its vastness and complexity. In this video, we embarked on a journey through the largest objects in the universe, from massive planets and record-breaking stars like Stephenson 218 to supermassive black holes like TON 618, and finally to the largest galaxies and cosmic structures like the Sloan Great Wall and the Hercules-Corona Borealis Great Wall. Each of these colossal entities is a reminder of the staggering scales and forces at play in the cosmos. The further we look, the more we realize how small we are, yet how interconnected we are with the universe's grand design. The journey from stars to galaxy clusters shows us that the universe is not just a collection of objects, but a tapestry of cosmic evolution and history, billions of years in the making. As we continue to explore, the universe reveals more of its secrets, and each discovery brings us closer to understanding our place in this vast, extraordinary expanse. Thank you for joining us on this journey through the largest things in the universe. Who knows what incredible discoveries await us next?